Okay. Thank you very much for the kind introduction. And first of all, I'd like to thank the organizers of the nice conference for inviting me to give this talk. It's a bit unfortunate that I couldn't be in Montreal in person, but hopefully this talk will be entertaining enough for you to, to enjoy the last day of the conference. Today I would like to talk about some of my recent works on Onsager algebras, especially in lattice models. But actually today I will not present actually a lot of results. Instead, I would just like to present some speculation, just some. Okay, perfect. Yeah. So today I am going to talk about some, instead of some results, I would like to just talk about some speculations, especially some questions that I personally do not know the answers. And these kind of questions that I have really originated from work that I've been doing with Vincent, who's probably in the audience, and Jules Lammers, who's now in Saclay. So the motivation that we had at the beginning was to understand, let's say, the spectrum or the Q operator for quantum spin 1/2 XXZ chain and at root of unity value of anisotropy. And for this kind of result, they are presented in this paper where we found out some kind of reminiscence of free fermionic structure in the spectrum, which I will present briefly later, which motivate me to have a couple of conjectures about a kind of a hidden Onsager algebraic structure in the second paper. And then later I wanted to generalize a little bit, and yeah, which is summarized in the last paper, which probably I won't have time to talk about. But before we start to talk about the question itself, let's motivate ourselves why we're interested in these problems. So first of all, I'd like to have a disclaimer that I'm a physicist, so I might not be very rigorous in some parts of the talk. So please forgive me if you're a mathematician. And so the reason why, as a physicist, we're interested in this is we would like to understand more about exactly solvable models. One of the most famous example is the Onsager solution to 2D classical Ising model in the absence of magnetic field, which has already kind of give lots of very interesting observations. At that time, of course, it's very new, and even nowadays, I think we still benefit a lot from these kind of observations. And the other thing which happens a bit later is the Yang-Baxter integrability for quantum systems, where we have these nice Yang-Baxter relations and so on. So today, basically what I want to convince you is that maybe these two are closely related. In a way that maybe we still need to understand better. And as a physicist, I'm interested in also in the quantum many-body physics, where especially we're interested in the out of equilibrium physics. For example, you can study the so-called quantum quench or periodically driven system, etc. And by studying these exactly solvable models, it gives us lots of valuable insights. For example, we can really solve the correlation functions after a symptotically long time in an analytic manner, which is very nice. So with that in mind, maybe we can take a look at one example which is exactly solvable in a trivial sense and also have some surprising features maybe. So the example that I would like to talk about is the spectrum of XX model. So XX model is defined for this Hamiltonian. Let's say we are not so worried about the boundary condition. Maybe we're going to take a periodic boundary condition, and they are just spin 1/2 that interact with the nearest neighbor in a one-dimensional chain. So this model actually can be easily solved. If you do a Jordan-Wigner transformation, you realize that actually this model is just a free fermionic model in this kind of tight binding form. And you can find out the spectrum very easily just by doing a Fourier transform. And you see that basically the energy is more or less like a cosine of the momentum of the particles. Or you can think of the magnons or fermions as you wish. But what is kind of nice is that for this dispersion, well, you can take let's say a particle with momentum k and pi minus k, such that if you excite both particles at the same time, the spectrum or the energy is not changed. So this you might find, okay, it's kind of trivial. But what it really says is that you have a huge degeneracies by exciting from, let's say, one state to some other states, just with the different pairs of momentum, since they are free, so they are not really going to influence each other. And they all degenerate in energy. And moreover, they also degenerate also in higher order charges, because it's integrable or it's a free system. And moreover, this Hamiltonian commute with the spin flip operator, which means this kind of towering structure is symmetric around the equator, which means it's like a zero magnetization, if you want. Okay, but looks all nice. But what happened if there's interaction? So what happened if we add some interaction to this model, and whether this degeneracy will survive or not? And this is really what we studied with Vincent and Jules, where we just consider an XXZ model where we add this anisotropy here, delta, which makes the model interacting. I will explain maybe in details how to solve this model later, but right now what we need to know is that this delta here, you can parameterize it in this way, such that this Q is an operator that can be chosen to be at values such as Q to some certain integer is 1, which is called the root of unity values. And when let's say when Q equals I, then we get basically delta equals 0, where we have XX model. But let's say when delta is 1/2, which means we are at root of unity, Q is exponential I pi over 3. And in this case, we look at the spectrum. We not only looking for the eigenvalues of the energy, but also, let's say, the whole transfer matrix. We still observe huge degeneracies. It's similar towering structure as I showed you for the free fermion case. The only difference is that there you need to excite a pair of excitations, but here you need to excite, let's say, 3 magnons in the same time at certain, let's say, values of so-called at roots, where all these states, they are degenerate in transfer. And this is actually later what I realized is that also these kind of states, they have some kind of reminiscence of free fermionic structure. Namely, you can add the excitation centered at certain momentum, and then you can do some kind of combinatorics that you can just get all the other excited states. Sorry, not excited, but degenerate states. This is somehow due to some kind of underlying Onsager algebra that are present in these models, which leads to these exponential degeneracies. Next, I'm just going to show you what is Onsager algebra, since I've been talking about it for the past few minutes. So this Onsager algebra is first used by Onsager to solve 2D Ising model. And it's an infinite dimensional Lie algebra where you have this generator A and J, where these subindices are just integers. And they satisfy this kind of, let's say, this kind of commutation relation where if you commute between A, you get J, and if you commute J and A, you get some further A. So you can generate more and more A. This has been shown by basically Davis, such that this Onsager algebra is isomorphic to the so-called Dolan-Grady relation, where you only need the first 2 A's. So you just need A0 and A1, and it is enough to generate all these J's and the further A's just as commutators between A0 and A1. And this Dolan-Grady relation reads as follows. So you have kind of a commutator between A0 and A1 3 times is proportional to the commutator between A0 and A1, and also for the dual version, which means you interchange the row of A0 and A1. And this is actually a very well-known result in physics called the Kramers-Vanier self-duality in this case. for example, there are many physical representations of this Onsager algebra that we care about. For example, the most famous one is the transverse field Ising model, where A naught is just sum over the magnetization, and A1 here is just a spin flip of two neighboring side. And okay, for this model, it's also you can solve with free fermions. But what is something which is very nice, maybe not so much mentioned in the literature before, is that this transverse field Ising model is actually closely related to the XX model that I was talking about. And also there's another kind of non-trivial example, which is the chiral-pulse model, where it's no longer free, it's fully interacting. And I believe maybe during Eric's talk, if you were there, maybe you already know what I'm going to talk about, but still, just to emphasize, we have some pulse-like pulse spin operator Z and X, which is defined as Z is like a diagonal with some roots of unity, with some Q, and this A naught A1 is really kind of a generalization of the Ising model, and the duality is there, and from the duality you can, for example, immediately spot that there's a phase transition at lambda equals 1, and the relation between transverse field Ising model and XX model goes as follows. So this is really I learned it from the paper by Eric and Paul a few years ago, where you can define your A naught and A1 as just in this way. So you have you just write let's say A naught is sum over let's say the even term, the odd term, and A1 is sum over the even term, where these kind of local terms, these anti-commute when they are neighbors. So when 2J would anti-commute with H2J minus 1 and H2J plus 1, etc. And then what you can get is you can construct this operator H U1 such that it's in this combination. So it's a product of the nearest neighbor. And I believe I might made a mistake here. So yeah, okay, it should be actually just 2J and sorry. So this should be this. Yeah, okay, never mind. And if you write explicitly, it looks like this. So this is actually quite easy. So it's just a sigma plus sigma minus sigma minus sigma plus, and this is also sometimes called spin current in XXZ model, for example. But it's not important where we get the name. But what is important is that this operator commute with both A naught and A1. And since we know that the Onsager algebra can be spanned just by A naught and A1, so this operator commute with actually any AN when A is an integer. Also, it commutes with all the J's actually. And moreover, you can think of this kind of this Hamiltonian HU1. It has not only infinite many conserved quantities, but also it has a conserved quantity that do not commute with each other, because A actually do not commute with each other. And the relation between this HU1 and the XX model is that up to some unitary transformation, you can get it back to the XX model. So this XX model, you can call it, it possesses some kind of hidden Onsager algebra, where actually the generators that you get from this A1, part of it will change the magnetization by because so this H of course commute with the magnetization. So this A1 has some part that change the magnetization by 2 and either more or less, and this really gives you this tower structure that the degeneracies that I showed you.
So I guess it's just a typo, but it's quite important. So I is J, is it in here? And this is HJ,
no.
J plus 1?
No, I square is -1. It's the imaginary.
Oh, okay, it is. Okay, fine.
Yeah, so it's not J. Yeah. So it's because if it's J, then I mean you will get yeah, it looks like some kind of boost operator, but it's not. It simply just has just like simple local density, just as this. Yeah, that's why if you do the transformation, you can get back to the you know, XX model, which is okay. You can also write sigma plus sigma plus sigma. Sorry, sigma minus sigma plus. And actually, this logic even works for a 3-state Cairo-Pulse model, where you would get this spin 1 homological Fatiev 19 vertex model at root unity alpha over 3, which is interacting. So this already gives us a little bit of hope that maybe we will be able to find some kind of Onsager algebra even in the interacting system, right? Because it also works for truly interacting spin chain, as showed by Eric and the collaborators. And in order to show you this, well, I need to go for a little bit technical part, which is I need to explain the integrability of XXZ model at root of unity. And here I use the so-called Sklianin's transfer matrix or Lax operator, where this Lax operator, let's say, is kind of, you can think of this transfer matrix defined by some Lax operator with different representation in the auxiliary space and in the physical space. And the physical space always be 1/2 for me. So basically, it can be written in the basis of the physical space as a 2x2 matrix, where for the element here, they can be on any kind of representation for the so-called nuclear SL2 algebra, which is can be summarized here. And what is important is that if you choose this A to be the fundamental representation, you get this transfer matrix, which at the log derivative is just the usual XXZ Hamiltonian. And now, of course, I need to consider some other objects other than just using the fundamental representation of SL2 in the auxiliary space. So in this case specifically, I would like to consider so I consider root of unity parameterized by this eta, where maybe I can write it down. So Q is just exponential of eta, such that Q to the power of 2L2 is +1, right? So we are really at root of unity. So if you choose this eta to be parameterized in this way. And in this case, when Q is at these values, the UQSL2 permits a L2 dimensional representation. Okay, one you can call it highest weight with complex spin, and the other you can call it semi-cyclic. The idea is to say that you can start with some kind of highest weight states, which you can get all the descendants by acting as plus. And moreover, if you are at kind of, okay, maybe you start with the lowest weight, and then you get the highest weight, you act as plus again, you get back to the lowest weight state. And this is called semi-cyclic, because if you have the other way, so if you act S minus at 0 to get S3, then you are at highest weight states. So here I choose the example of L2 equals 4, I guess. And moreover, I have another kind of complex parameter S to tune here. So S can be any complex number. And when beta equals 0, so you don't permit the highest weight to talk to the lowest weight, then you get the so-called highest weight representation. And now I just use this representation into my, you know, as my Lax operator, and I want to find out what is the, I would like to find out what is the kind of Young-Baxter-like relation for this semi-cyclic representation in the auxiliary space. And what is happening actually is quite interesting, because it's not really Young-Baxter relation. So the what one can prove is that you need another parameter called epsilon, where this epsilon is Q to the power of L2. So as we were saying that Q is exponential of I pi L1 over L2. So when L1 is, let's say, even, then obviously this epsilon is just +1. But when L1 is odd, then basically Q to the power of L2 is -1. And with this information, then what we can prove is that, let's say the R here is just acting on the spin 1/2 space. So it will be this one. Well, it intertwines between this L with the, it will kind of interchange this parameter beta by some epsilon, either it's plus or -1. So if epsilon is +1, of course, it's just the normal Yang-Baxter relation. But if epsilon is -1, you will see that actually you would kind of interchange plus beta with minus beta and vice versa. And this you can draw a diagram, which is shown here. So which I omit some actually quite important ingredient, which is the twist, because I'm considering actually a quasi-periodic system. But we can imagine that this twist is 0 in this case. It will not change too much of the conclusion that I will arrive. And in that case, well, I define this kind of semi-cyclic transform matrix in this way. So it has some kind of different sign at the even and odd side if we have epsilon is -1, of course it's +1, then it's trivial, so everything is plus. And what happened is that you can kind of intertwine this with the so this transform matrix is the one with the fundamental representation, so spin 1/2 in the auxiliary space, by changing the sign of this beta. Or in a nutshell, you can see that you start with this T acting with this transform matrix with the fundamental representation. What it does is when you drag it to the other side, you get epsilon. So one thing that immediately you consider, if epsilon is +1, they commute. And this has been observed in a paper by Persen, maybe around 2004. And when beta is 0, it also commutes, regardless of the root of unity, regardless of the value of epsilon. And this is known even a bit before. So with these two properties, you can try to define some charges, because since we have a transform matrix, well, we can expand it over some parameter. One naive way to do it is to expand over this complex number U, which is associated with with the transform matrix. Actually, you can also expand over this S, which is also a complex number, or with this beta. And indeed, you consider these two, one called Z, the other called Y, where it's the log derivative with respect to the complex number S or complex number beta. One thing that you see is that here, this Z commute with sigma Z, the total magnetization. So it does not change the magnetization, while this Y here, it changes the magnetization by unit L. And in the case when epsilon is +1, you can easily show that Z and Y, they commute with the transform matrix. So it is a good charge of your Hamiltonian. On the other hand, if you have epsilon is -1, Z still commute, while Y, it kind of anti-commute with the transform matrix. You might think it might be a problem, but actually it's not, because what it does is it will add a pi momentum to your system. And this is very similar to the fermionic case, when you excite K and pi minus K, the total momentum that you did. When you do the two excitations, you add a total momentum of pi to your system. And this is very similar for this Y charge here. In that case, you can, you have this Z and the U. And you might worry about the locality, which means whether it has a well-defined local density, because the Hamiltonians, for example, have a well-defined local density. And indeed, in this case, when L2 is larger than 2, what you find out is that the density is not really local, but they are quasi-local. Namely, it involves all terms that has like a long-range interaction, but the coefficient decay exponentially. So it still has a pretty well-defined thermodynamic limit. What I find is really surprising is that this has a direct relation to Onsager algebra. So for example, let's take our favorite XX model, which means L2 equals 2. Here we can do the expansion over this Z and U. What we find out is that this Z naught can be written in this way. Okay, which is a spin current, which just it's just some coincidence. It's not really, because the point is, if we do the transformation back, we should recover what we have for the X for the Ising model, but doesn't matter. So we have the Z naught and Y naught, where Y naught changed the magnetization by 2. And what is really nice is that what is really nice is that if you sum over Z naught and Y naught plus Y naught dagger, this is nothing but the A1 in the Onsager algebra, where A naught being the magnetization. And if we do the unitary transformation that brings XX model to the spin current, this A1, if you do that, it will become basically sigma X term. And also you can check that they satisfy Dolan-Grady relation. So this is kind of a way of finding Ising model from XX model, where you just compute the Z, so-called Z charge and Y charge. In this case, they are all local density, and you combine them in this way, and then you get Ising model. And then what's really interesting is that you can do exactly the same manipulation for L2 larger than 3. And in that case, you cannot get a nice expression as kind of this one, because the operator is quasi-local. But nonetheless, you can test it on a computer, let's see, and and then you can just try to combine in the same way as in the XX case. And what you find out is that indeed it still satisfies Dolan-Grady relation, which means it is a representation of Onsager algebra. Of course, when I increase system size, this relation will not change. So that brings me to this conjecture, such that there is actually a hidden Onsager symmetry in all quantum XXZ model, or if you are from StatMech 6x model at root of unity, when the twist of this quasi-periodic condition is some specific value, which if you really want to find out what that is, you can read our papers. Okay, so here I would like to make a few remarks. So first of all, it also works for higher spin generalization, and this you can do by doing a transfer matrix fusion. For example, you can get the spin 1 case, which is 19 vertex model discussed by Eric, and you can also for example, get even higher spin generalization, and this thing will not change. And another thing which you can get for analytically, which is to get this Z naught and Y naught for the 19 vertex model at root of unity R/3, where they are also kind of in terms of local densities. And there you can prove Onsager algebra analytically. But for let's say for root of unity, which is not let's say arbitrary root of unity, it's I don't know how to prove it, but at least from the numerics, I'm very convinced that this will happen. And also from the structure of the spectra that really give us a very good hint. So in order to, if we really want to prove the conjecture, well, we need to find some connection between Onsager algebra, which in the mathematical sense is a classical Lie algebra, and somehow some relation to the quantum group structure which is intrinsically quantum in the mathematical sense. But one thing that I would like to emphasize, which is that the periodic or quasi-periodic XXZ model of root unity, it's not really invariant under UQSL2 algebra. So because of the periodicity, somehow we are breaking the true quantum algebra, and that's probably maybe the reason why we end up with actually a classically algebra. And so there are also many papers, especially by probably people in the audiences, where they find out that this UQSL2 invariant XXZ, so XXZ model at root unity with open boundary condition, sort of open boundary, so or certain with a certain boundary magnetic field, is closely related to the so-called Q Onsager algebra, which can be considered as a Q deformation of this classical Onsager algebra that I presented today. So it's really kind of not so clear to me how this is related to this kind of hidden Onsager algebra structure that I presented to you. So yeah, so there are still many let's say many things to be understood in this, also in this side. And one thing that you might also guess what I would like to do is to find out that whether we can generalize this Onsager algebra. And turns out that yes, we can do it. There has been papers already in the 90s, for example, by Uglov and others, where they presented the Onsager algebra as a sub algebra of some quantum of some affine Lie algebra. And this also recently has been summarized very nicely by Stockman, where he presented relatively general framework on how to do this. And you might wonder, okay, from mathematics we understand what's going on, but could we find actually some physical models that has some relation to this generalization of Onsager algebra? And the answer is yes. For example, we know that there's Ising model, which is free fermionic, and recently Paul Findlay has studied the so-called a model called free fermions in disguise, where you also have a completely free spectrum. Meanwhile, having let's say instead of kind of Ising-like interaction, it's involved with 3 spins, etc. And there, what's happening is that, okay, for Ising model, you not only have Onsager algebra, it's also free, so it has this Clifford algebra, which also is related to a quotient of a Templin-Lieb algebra, and this can be really generalized into some generalized Clifford algebra, which Findlay's model is related to. And there you kind of automatically obtain a generalization of the Onsager algebra there. But okay, I will not talk about that today. If you're interested, you can look it up. And I guess that's all what I want to say. Just let me conclude. So today I showed you there are many physical related representations, if you wish, or models of Onsager algebra in quantum lattice models such as Ising model or parapods, and moreover XX or XXZ model and its higher spin generalization. And motivated from this and the study of XXZ model at root unity with quasi-periodic boundary condition, I have several conjectures about the hidden Onsager structure there. And what's really kind of remaining to be an open question to me, first of all, is how to prove it. And secondly, what is exactly the relation between the integrability or quantum groups to this Onsager story? And possibly, if you were at Eric's talk, maybe he might give some answer to this question. And lastly, I briefly showed you that you can actually have generalization of it. For example, you can study the so-called Findley's model or free fermions in disguise. And actually, this model can even be generalized even further to certain using graph theory. So actually, using graph theory, you can prove or you can find even more seemingly interacting models that has free spectra. And these models, I presume that could, in principle, could also be understood using some kind of Onsager-like algebra. And another thing which, okay, maybe it's not really related to this topic, which is like whether we can get some kind of to relate this graph theory theoretical construction to the maybe more StatMag like a vertex model, etc. And this probably will be remain for the future discussions. Yeah, that's all. Thank you very much for your attention.
Thank you for this very nice seminar. Question?
Can you hear me correctly?
Right. Yeah, I can. Yeah.
Okay. So I was wondering if you're familiar with the papers by Deguchi, Fabrice, and McCoy from the early 2000s. So
yes. Yeah, I can comment on this. Yes. So of course, one of the this is a bit back to this slide where basically what Fabricius, McCoy, and collaborators, what they also studied the spectrum of XXZ spin chain, and they also find this degenerate structure, and what they conclude, and that's actually why I call it FM, because it stands for Fabricius McCoy. I mean, if you can see, it's a bit small, but it doesn't matter. And what they attribute to is they attribute the degeneracies to the so-called SL2 loop algebra. But there's a little bit of a caveat in their argument, which is they have, strictly speaking, SL2 loop algebra for fixed magnetization. So they have an algebra which works for, let's say, this set of magnetization. So if I have m equals 1, you still have degeneracies, but then you have to have a new set of operators that satisfy this, let's say, a different SL2 loop algebra. And what this Onsager algebra was saying is actually very similar, because Onsager algebra is actually a subalgebra of SL2 loop algebra, first of all. And moreover, the Onsager algebra that I conjectured, it works for all the magnetization. So it's kind of, I think in a way, it solves one of the caveats that Fabricius and McCoy et al. Was saying. So basically, they were saying that their SL2 loop algebra for fixed magnetization, which is true, but what it is really is a manifestation of the Onsager algebra that works for all magnetization. Yeah.
Okay, so in the end, this Onsager algebra will be realized in terms of the renormalized S plus. Oh, sorry, there's some sound. Yeah. So these Onsager generators will be realized in terms of the S plus and minus.
That goes beyond my.
Oh. Okay, so if I end my question, yeah. So these generators of your Onsager algebra, you'll be able to write them in terms of the renormalized S plus, S minus powers of Fabricius and McCoy. Is that correct or not?
Yes. Yes.
Okay.
You can. Yeah. It's a little bit subtle, but more or less you can. Yes. I mean, the point is, for example, for this example, it is quite obvious what this operator in terms of the S plus and S minus operator that Fabricius and McCoy wrote down. But what is a little bit subtle, which is my operator that there's some kind of creation operator for this state and this state, and it's kind of a superposition of this S. So if you naively acting this S plus and S minus from Fabricius and McCoy, from this state, you will get a linear superposition of all these states. Yeah. But we have a reason why these states are better, because it diagonalizes this z charge, this this z operator that I showed you, instead of So basically, the S plus and S minus from Fabricius-McCoy, it will not diagonalize this z charge, but these operators will. So there exists other operator which relate to the y, which will diagonalize this this additional charge, which was not discussed by Fabricius and McCoy. Yeah.
I have a similar question related with Fabricius Deguchi-McCoy paper. So I thought the main difference between their model and your model is that you take the twist. You have a twist.
Yes, but I can set the twist to 0. Yeah.
Yeah. So in their case, it's twist to 0. So I thought the fact that they had this loop SL2 algebra symmetry will become this Onsager algebra symmetry. But what you just explained is that their loop algebra is restricted to the case of these magnetization values, right?
Yeah, but okay. To be fair, they consider different set of magnetization values.
But then
I cannot say that it's not really the same, because if you consider all the magnetization values, it should be the same.
Yeah, but then what is the role of the twist in because it's
so these degeneracies only appear when the twist is we call it commensurate values. For example, let's say you have even side and twist is 0. This will always work. It always have these degeneracies. And if you have twist is it can also be some integer values of this eta. So if the twist is, let's say 2 pi over 3, it might also work. We summarize like a formula in our paper with one sum. So about like under which twist there will be these degeneracies.
Okay.
Yeah, because usually what you can do is you add an infinitesimal twist. Well, it will lift the degeneracy, right? But what happens is if it lifts away and at some point it becomes degenerate again. So that's if you really numerically tune this parameter, that's what you will see.
So I wanted to ask about your RLL relation that this Onsager algebra came from. So this looks like a kind of mixture of a regular RLL relation and a dynamical RLL relation, in the shifts in the L's, but not in the R. So can you view it as some sort of limit of the dynamical Yang Baxter?
That's a very good comment. Okay, honest answer is I do not know. So possibly this is like a limiting version of so certain limit of this dynamical Yang Baxter. That's possible. Yeah.
Okay, thanks.
Yeah,
no in that case, you may expect also a shift in the R matrix somewhere, at least in one side.
Shift in the R matrix.
Yeah, I mean
not all L's are shifted. Not all L's are shifted.
Well, you'd have in the RLL relations, you get a shift in all three terms. There are R and L shifted. Half of them are shifted and half of them are not shifted. Right.
No.
Yeah.
Right.
Yeah.
It's
yeah.
not
this
really...
one shifts in the L's and those shift in the R.
Yeah.
So
it's quite different.
Oh, okay. Sorry. Thanks for the comment. Yeah.
Other comments, questions? So let the speaker again.